Frank's new book, Fundamentals, 10 Keys to Reality, is coming out next week on the 12th. And Frank's book is remarkable. I can say that as always. His other books have been such inspirations for Patty and me. And tonight's Salon is really kind of your impressions of what reality has taught you. And we're kind of interested in the conversation. How the format's going to go is that we'll let Frank make his comments, and then afterward we'll have questions. And how that goes is you can ask your questions in voice or text, and I'll be the moderator. So if you don't know Frank, Frank is writes a monthly column at the Wall Street Journal. He's a faculty or has appointments at MIT, in Stockholm. There was an institute in China named for him. He's at ASU based. You know, something that I think is really interesting, you're an early MacArthur winner. Goes on and on, Frank. And I think you're on you have one, but I'm anticipating you'll have 2 or 3 more Nobel Prizes before too long. So
that's optimistic. 1 or 2 maybe.
and we could go into those, but it's absolutely great. And I'm going to now turn it over to you, Frank. And
very good.
Thanks.
Thank you. So, as Thomas said, okay, now we'll see if this clever person can manage to share the screen. Okay. And get the presentation. Okay, can you hear me very nicely and see the white screen?
Yes.
All right, great. Okay, so the subject tonight is what reality has taught me. I'm not going to be able to exhaust the subject tonight, but I will show you some of the things that reality has taught me that are broad lessons. I'm not going to tell you about the specific equations or technicalities or the puzzlements of deep quantum theory, but lessons that really have broad philosophical implications that really are kind of answering the questions that I asked myself as a teenager and when I was getting into science in the first place, and trying to get replacements for the Roman Catholicism that I no longer could subscribe to, and also that many of my friends who are not scientists, lawyers, doctors, and people I meet in everyday life have asked me about, because they think that people who study physical reality for a living can help tell them something that they don't know about how the world works, and they're right. So the first huge lesson that reality has taught me is humility. You've probably all seen some version of this picture of the Earth from space, and this is taken from the surface of the moon. You can see on the base, and the Earth as seen from the moon is just about twice as large as in diameter as the moon seen from the Earth, but still occupies a small part of the sky. The moon has no atmosphere, so the rest of the sky is really dark black. And everything we have struggled with in humanity, all the wars, the upsets, the history, the triumphs, all is playing out on this little marble in the sky. Foreign relations are all about what's going on, connecting different parts of that little planet. And that little planet is part of our solar system, which is dominated by the sun, and the sun is a kind of star, a very typical kind of star. Our galaxy contains about 100 billion such stars. And then if you go further out and look through the Hubble, this is a picture taken by the Hubble Space Telescope of a narrow sliver of the sky, but going very deep to faint objects. You see that when you look at faint objects and go deep, the sky is no longer dominated by stars, but by galaxies. And each of these galaxies is comparable to our own Milky Way galaxy. And this, I think, is something like 1/3 of 1 degree of the sky in all those directions. So the universe is really, really, really large. And the Earth within it is very tiny, and human beings within the Earth are tinier still. So there's lots of room for humility. And as it is for space, it also is for time. A dramatic way of looking at that is to compress the history of the universe since the Big Bang into the time scale of a single year. So the universe is about 13 billion years old. So you have to compress by a factor of 13 billion, but it makes these large numbers that otherwise would seem so alien, it sort of makes them come alive when you put them on a more human, manageable time scale. So the Big Bang starts on New Year's at 13.8 billion years ago. The oldest kind of objects we can see in the sky as individual objects are gamma ray bursts, and they were not terribly far from the origin of the universe. They occurred on 14th of January. The first galaxies started to form on the 22nd of January, and so forth. And so all this is happening in the absence of Earth. So not only in the absence of human beings, but in the absence of Earth. Earth starts to form about 4.4 billion years ago. We have rocks that stabilized then, and before that, the Earth was a gas cloud, and then briefly, on these scales, briefly a molten ball. But we have rocks from almost the very beginning, 4.4 billion years ago. So that was the 6th of September. The year is running out. It's already getting into fall, and Earth is just formed. Okay, life begins not long after Earth forms, and various things happen. I won't go through the list, but the kind of life that we're familiar with, that gets beyond simple bacteria and related one-cell forms of life, is already well into December 5th. The things that we think of as life on Earth in our environment, simple animals, fish, and so forth, take you well into December. So we're getting close to the end of the year. Dinosaurs dominated the Earth until about Christmas time. And then they were the great extinction event, which wiped them out and made way for a recognizably modern Earth occurred at 6:24 p.m. on December 30th. So all of human history is compressed into less than a day, much less than a day, actually. All of the time when mammals dominated the Earth is basically one day. Lots of room for humility. So that's one thing you certainly learn by studying physical reality. Uh, Individual humans are very, very small in space and time and not impressive objects on the scale of the universe. The other thing, however, that you learn that's the opposite in some ways that I've learned is chutzpah. That word may not be familiar to all of you, so I pulled down the definition. It's the quality of audacity, for good or bad. It's prominent in Yiddish, and if you grew up in New York, where I did, you would hear chutzpah quite a bit. And I've been accused of it also many times, so I know the word chutzpah. Then, although we are small, yet we are very complex. Each human being can support enormous numbers of atoms. The number of atoms in our body is comparable to the number of stars in the visible universe. And then the really powerful units, neurons, which power our thought processes and our ability to process information, of course, contain many atoms, but we have about as many neurons as there are stars in the galaxy. So we have lots of room for complexity, and you can quantify also how fast we think. Okay, so on the time scale of the universe, our lives are very short, but on the time scale of how long a thought, how many thoughts we can have, how many meaningful thoughts, I estimate that we have several billion opportunities to think. There are many ways to approach the question of how fast we can process information and how many thoughts we could have. One that I like, they all lead to roughly the same estimate. It's of course, the answer can't be more precise than the question, but one way that I like to think about it is you know that motion pictures are actually a sequence of stills that are shown very fast, one at a time. And so you can, and if they're shown too slowly, they do begin to look like a series of still shots. The continuity breaks up. So that shows how fast we can resolve information and get separate images out of things that are going by very fast. And the rate is about 40 a second. So so we can process about 40 separate images a second. And if you ask how fast can people play the piano and how fast can people play speed chess, you get all roughly the same kind of thing. And each of those leads to the conclusion that we can have several billion thoughts in a lifetime. So although we are small compared to the universe, we have lots of time for thinking and enough room to have very complex patterns that house meaningful patterns that are the physical substrate, the material substrate of mind. This is a picture by a famous neuroanatomist, Ramon y Cajal. This is the human hippocampus. So this is where short-term memory gets processed into long-term memory. A famous patient, M, who had lesions in the hippocampus, could not lay down any new long-term memories. So although he could still function, if he was introduced, he got newly introduced to the people who cared for him every single day and didn't recognize them an hour later. So this picture, by the way, well, you can see it's tremendous. It looks tremendously complex. The hippocampus is about the size of a walnut. This picture is made with a dyeing process that dyes very selectively only a small number of a small fraction of the neurons. That's why the picture can look sensible at all, because they overlap. If you dyed all of them, it would just look like black. But you can see that even with this selective dyeing, which turns about 1 in 1,000, I think, of the neurons black, you can see the regular patterning and just the proliferation of connections that make this little computer module or chip inside our heads. And we're very small in the universe and have a limited number of time. The spaces and the times of the universe unfold and swallow us up like specks. But by the power of thought, we can comprehend the universe. So I can talk to you about the universe and show you how big it is, and talk about how how long it's been around, and we can imagine those things and live through them vicariously, because we're large enough to support enormous complexity and have the chutzpah to think that we can try to understand it. And we've succeeded. The proof, so to speak, is in the pudding. If you look at the world GDP per capita, that is how much wealth per person there is in the world economy. And again, this is something that is tricky to estimate, but experts agree on these figures, at least within a few percent. And you see that since the lessons of the scientific revolution started after a long period of dormancy, once the lessons of the scientific revolution and the technology that came out of it were digested and put into use, starting in the mid 1800s, really, with the development of electric and technology and steam engines and so forth, the world GDP has gone up exponentially with no end in sight. So we've understood our world well enough to start bending it to our purposes, both for good and bad. The good news is that we're nowhere near exhausting the wealth of energy that we get from the sun, and the wealth of material that's around in the universe. The bad news is that our ways of exploiting it are also poisoning our atmosphere and having some nasty effects, and our power to make things go boom also has put us in danger. So this power is impressive, and we're beginning to disturb at least our little corner of the universe in ways good and bad, but impressive. So the world is comprehensible. It's our ability to control it is the proof. And the way that that's happened, the details of the kinds of theoretical ideas, the mathematical approach, the analysis by doing precise experiments on little things and then building back up after you've determined the basic laws, has really worked. Why it should work? I don't even know what an answer to that question would look like. But surely we don't have an answer. The best response, I think, is Einstein's, which is that the most incomprehensible thing about the world is that it is comprehensible to these little parts of the universe that we represent, that our brains represent. Another thing that I've learned is that answers breed questions. So as we've learned more, we've learned to ask better questions by knowing that the universe started in a Big Bang, and we can understand the outlines of cosmic history and ask details about how things originated. And we can ask ultimate questions about how the universe as a whole originated. We know lots of sub-answers, but each sub-answer leads to more ambitious questions about ultimate origins. I'd like to show you just very briefly a couple of frontiers of questioning now, which illustrate how great questions lead to great answers lead to great questions. When astronomers looked out on the sky with the Hubble Space Telescope and other instruments of that kind of power, they saw some very odd things. For instance, that if you point your telescopes in certain directions, you see that there are identical galaxies. That is, their spectra, their electromagnetic properties are identical, which is like two people having the same fingerprint. It just doesn't happen unless they're actually the same. So you see 5 different galaxies here that have the same fingerprint, and here another 3. This would have been really shocking, except that it was predicted. In Einstein's general theory of relativity, you learn that matter can bend light, but gravitationally. And so it's like looking through the bottom of a soda bottle or any kind of object that bends light severely. Sometimes you get multiple images. And so here's a galaxy. If it goes straight through to Earth, you see one image, but it can also have light originating from that galaxy bent and coming in from an angle, and you reconstruct that as looking as if you had a galaxy out here, a virtual image of the galaxy in a different place or a different place. And so this so-called gravitational lensing phenomenon explains why you can get these multiple images, and allows you, because the amount of bending is determined by the amount of gravity that has been exerted on the light, allows you to determine what the mass of these intermediate objects are. And when astronomers did that, they've found consistently, and in this way of estimating things, but also in other ways that don't involve lensing, but stars moving around galaxies and other things, consistently that there's an extra component of matter that does not have other astronomical signals. The only signal that's been seen is the fact that it exerts gravity. This is the so-called dark matter. It's not dark. Dark means that it hasn't, in this context, means it's completely transparent. It doesn't seem to have any effect other than causing gravity. This is not something that's acceptable to physicists. We want to know what else it does, and why it should be part of the universe. By the way, if you estimate the total amount of mass in this so-called dark matter, it's about 6 times as much as the kind of matter that we're made of and have been studying in the previous centuries of science and before, and that we've encountered. So the kind of matter made out of electrons, photons, quarks, and gluons that is the matter that plays a role in biology, chemistry, and all forms of engineering. This is something else. It's definitely, we don't know what it is, but we know it's definitely not that, because ordinary matter has the wrong properties. It would have been seen by astronomers because of their cleverness in detecting ordinary matter. So what is it? Now we have another mystery in physics, which at first sight has nothing to do with the dark matter problem. That is a very peculiar property of the law, the basic laws of physics, is that they look almost the same if you run them backwards in time. So if you run a movie of everyday life backwards in time, it doesn't look like everyday life, of course. But if you focus on a very small part of matter, so deep within a liquid, in water, for instance, or certainly if you look at subatomic events, if you took a movie of what was going on and ran it backwards, you wouldn't be able to tell that it was not a legitimate movie. The movies run forwards and backwards, obey exactly the same laws, almost. For practical purposes, exactly the same laws. And the big question is simple: why? Why should that be true? And by a long chain of reasoning, which I won't even attempt to convey, although I'm of course be more than happy to discuss it when we have questions, trying to come to grips with that question leads us to add a new form of matter, which kind of maintains the balance between past and future. And that new form of matter, which we call axions, has exactly the right properties to supply the dark matter. It gets produced in the Big Bang, it's stable, it interacts very, very weakly with ordinary matter. And so those great answers about what's out there and what are the basic laws has led us to a great question of what is this dark matter and a possible answer. And a lot of what I've been doing recently is trying to figure out ways of making these axions visible. This is a cartoon version of what that looks like. So you want to convert axions into things that we can see, which theoretically happens in the presence of a magnetic field like that. So, and we'll find out. Another great question. The other one I'll mention in this little introduction, in this talk, is everything we've learned in our investigation of the universe is consistent with the concept, what Francis Crick, the great biologist, called the astonishing hypothesis, that the material basis of mind is matter, that mind, human brains are the embodiment of human mind, and there's nothing else, that's really an emergent property of matter. This is certainly the working hypothesis of neurobiology, and so far hasn't failed. And physicists who do very delicate experiments and have to shield their labs from stray radio fields and shaking of the earth or little variations in temperature and so forth, have never had to make any allowance for what people are thinking. So it seems that there's no separate power of thought to affect matter that's not captured in the laws of physics. At least that's the astonishing hypothesis. But it's very counterintuitive. It certainly doesn't seem, it certainly seems that there's a separate thing, a will, a mind, and we don't understand the mechanisms of how it works in great detail. And in some cases of consciousness, for instance, we only have vague ideas of exactly how it works, but we're faced with these great answers about the origins of heredity and metabolism and many biological processes that were once thought to be mysterious, and our ability to build artificial minds that's become so refined and has given us kind of models of how mind can emerge from matter. Those answers have generated the ability to take on this great question of how and whether mind emerges from matter. So another thing that I've learned in my love affair, now extending over several decades with physical reality, is that great answers lead to great questions. Another lesson I've learned is a concept called complementarity. This is the concept that different descriptions of the same thing that conflict with each other, or at least interfere with each other, may be necessary in order to do that thing justice. So a beautiful example of this, which is actually very closely related to Heisenberg's uncertainty principle and the inability to measure both position and momentum of particles, is in music. You can analyze music harmonically. So you look at each slice of time and see how many notes are playing and which notes, or you can analyze it by looking through time. So averaging, or not averaging, but synthesizing the behavior over many times, but separating out the different voices so that you have the melodic aspect. So you take apart the harmonies and look at the melodies. Both of these are important ways of looking at music, but you can't do both at once. You can either synthesize the times and look at the lines, or you can take them apart and look at the many notes playing at the same time to get the harmonies. And the interplay of these two things, for instance, is what makes the whole thing more than the sum of its parts. And to do justice to it, you have to do these complementary analyses. And I think part of the magic of polyphonic music, and for instance, the music of Bach, you can sort of feel it, that both of these things are happening at the same time. And there's more than you can take in all at once. Here's another more humble version of complementarity that is quite cute. What is this? Is this a rabbit or a duck? Well, if you look at it one way, it looks like a pretty good duck, but it's also a rabbit. And either description is bringing something to the table. So they both have a certain validity, but you can't apply both at once. There's no such animal. So that's an example, another example of complementarity, the rabbit duck. So I wanted to keep this presentation short so we could have discussions and questions, and take the things in whatever direction you like. But let me just say that there's lots more that I've learned from the universe and physical reality. And if you want to see much more of what I've learned and conveyed in the way that I've conveyed it, this book that Thomas mentioned is now about to enter physical reality, and you can order it. It's Fundamentals, 10 Keys to Reality. People have said very nice things about it. Sean Carroll, Ramakrishnan, Steven Pinker, Paul Davies, Krista Tippett, et cetera, Steve Strogath. Yeah. And even most of these things they said even before I put guns to their head. So, and here's I won't go into this, but into the contents of the book in any detail. But I just want to advertise the approach, and this also I hope could stimulate some discussion. It says 10 keys to reality. I tried to extract 10 big lessons from what I've learned about physical reality that everyone can understand, and everyone, I think, every thinking person would be interested to understand, and that can add to your appreciation of the universe and how you experience it, and not just the universe, but everyday life. So it's in two parts. These are the chapter titles. Each one is kind of an assertion, a key to understanding reality. So one is there's plenty of space, which we've discussed, both in the sense that there's plenty out there, but also plenty within. There's plenty of time. there are very few ingredients. I didn't talk about that, but the basic laws of physics tell us that there are very, very few ingredients out of which you can build up all the kinds of matter that we know about, and form the foundation, together with the laws, for that tremendous growth of our ability to control nature and create wealth. There are very few of them, so I can actually tell you all about them in meaningful detail. There's plenty of matter and energy. Similar, this is a little more abstract than space and time, but only a little, and is both humbling, but also very optimistic about the future. We are nowhere near exploiting the full range of resources and the possibilities for creating new levels of wealth and complexity and intelligence are only beginning to be tapped into. So that's what there is. And then the second part is about origins and what it all means, so to speak. So one thing I try to convey is that cosmic history is an open book. I told you that there was a Big Bang 13.8 billion years ago. How do we know that? What does it mean concretely in terms of things we observe? And it's actually quite convincing and quite simple, and I try to convey that. That leaves us with a great question. And again, this is an example of how great answers lead to great questions. If the universe is so simple in some sense in its origin, and the laws are simple, how did the world get so complicated? Okay, why is the history of England so complicated with all the kings going back and forth? For instance, how did a complicated universe arise from simple basics? That's a very interesting story that you can get a grip on. And then there's plenty more to see. Our knowledge of the laws tells us that our natural senses actually sample only a very small part of reality. And so there are wonderful opportunities for expanding our senses, for opening the doors of perception, in the words of William Blake. And these can be either practical things or huge projects like the Large Hadron Collider or the Hubble Space Telescope that open up new things to see, and we design them in advance and they work, and we can do a lot more there too. And mysteries remain. I told you about the dark matter, and that's one that I go into some depth about. There's also the great mystery of how mind emerges from matter, which I try to focus on. And then finally, that sort of summing it all up and extracting lessons about about questions that are usually thought of as philosophical or even theological. The idea that complementarity, that different ways of thinking about the same thing can both be valid and both be important, even though they seem to conflict or do conflict, is a way of expanding your mind, and also teaches you, I think, tolerance, and that you should try to understand other points of view rather than trying to conquer them or dismiss them or shut them out. So that was my introductory talk, and I hope it opens up some questions in your mind, as well as the desire to buy the book. I'll turn it over to Thomas as our host to go to the next stage.
That's great. Frank, do you want to stop sharing your screen so we can?
Yes, I will stop sharing my screen.
That's great.
For my own benefit, I'll also stop the presentation so I can see the rest of you and see your questions.
before I,
Okay, so
before
we
I,
do have, well, Thomas, you're going to moderate, I guess. So.
well, I'm going to jump in with a question
Mm,
before everybody else, because you talked about axions, and I think a lot
mm.
of people here tonight might not realize that axions are your own idea, and they are
Yeah,
the leading idea of what dark matter is. And this is
I
why.
think yeah, I think after many years of it being a kind of cult, small cult of fanatics who believed in axions, as sort of other ideas have been discredited and axions look better and better theoretically as we understand them better in this role, and also that they really do solve that problem about time reversal symmetry, that they have become the leading. I think that doesn't mean it's right, but it does mean that among people who sort of have the right to have an opinion, uh, they are the leading candidate for what the dark matter might be. And the theory is sufficiently specific of how they should behave that we'll know them when we see them, and we can also try to design suitable antennas to do that. And that's an ongoing endeavor around the world with thousands of PhD physicists involved, including me very much. So, watch this space sometime in the next decade or two. One of these efforts might succeed. We know it's very difficult. I mean, dark matter is famous for being difficult to see. So if it were too easy to see, that would be wrong. But we can build these special purpose antennas. I should remind you that in the mid 19th century, when Maxwell proposed the theory of electromagnetic waves, no one had ever seen a radio wave. No one had ever uh, uh, or even suspected its existence, or X-rays or microwaves that nowadays we cook with. Uh, and suitable antennas and generators and detectors all had to be designed based on the equations. And we're in a similar, I think we're maybe 200 years behind in axion generation and detection, but we'll get there if they exist.
If I can jump in with a second part, and that was your idea of complementarianism. And something that you've talked with Patty and I about is how we see the world, like how we see a table or a chair one way as maybe different from another way of perceiving that. Could you just mention a little bit about that?
Well, there are many ways in which complementarity applies to the basic perception of the world. Uh, Let me tell you a couple. So one is very physical. That is, if you look in very dim light at objects, so that the light so that the light is really barely detectable, it's broken down into individual photons. Uh, you will see flashes. You won't be able to maintain the illusion of continuity of the light stream. And not only will you see flashes, but the flashes you see will be entirely different and distinct from the flashes that somebody else sees. You'll never see flashes at the same time because you're seeing different photons. So your perceptions of the world are entirely different, and yet they are applying to the same object. And so that's one example out of many of how quantum mechanics forces you into viewing things in complementary ways. Uh, I'm not sure what you were getting at with your question. Can you,
Oh,
do you want to make it more specific or?
yeah. I mean, go ahead. Do you have? No. What I was thinking, Frank, was that on one level, there's a world of atoms, or on the atomic
Oh,
level.
yes. Oh, okay. Yes, right. So,
And
yeah. So one way of dealing with the world and perceiving things is sort of the hardcore physics way, is tracing things down to their most basic units, atoms, elementary particles, quantum fields, understanding those things thoroughly, and then trying to build back up. And we can do that well enough in simple cases to check that the description really works, and it's enabled us to design transistors and technological devices and so forth. But on the other hand, the cases in which we can actually solve the equations are quite limited. If you wanted to describe the behavior of a human being or the behavior of a stock market or anything of that level of complexity, or even much more modest levels of complexity, but let's talk about those. You need entirely different concepts. If I tried to figure out what Thomas is going to say or what Patty is going to say based on knowing the atoms and quarks and so forth inside them and what they were doing, I wouldn't be able to do it. Its computations are too hard. It's actually not just a matter of practicality, it's a matter of principle, because the ultimate description involves wave functions, which you can't know completely because of the uncertainty principle. So it's not an appropriate description. And yet we do have descriptions of what people are and how they act based on entirely different ideas that are very useful and accurate in predicting some aspects of behavior. That can be surprises, but we more or less predict how people are going to behave, how they're going to respond to our actions. And that's a different description that uses concepts like free will and mind that are different from the physical concepts. Yet they both apply. They're both valid. If you want to design drugs for the same human body that you want to think has a mind and a will, you have to think about the physicality of how the mind works also. So these are both valid ways of addressing different questions that you have to use both for practical reasons and for reasons of principle in order to do justice to what a person is. So
Great.
that's an example of complementarity. So questions like, do we have free will, or is it all determined? Or is there mind, or is there only mind or only matter? These questions, I think, are bad questions that you transcend when you appreciate the principle of complementarity, that different kinds of questions may require different concepts to address them in insightful ways. So even though they're talking about the same thing, these concepts can only be applied separately and appropriately to different kinds of questions.
Great, thank you. I'm going to read a couple comments before I take, there's the first question, but Joe wrote a comment, interesting tidbit, going back to your earlier discussion. The reason it's so difficult to remember dreams is the hippocampus is offline for most part while we sleep. And then the second comment was from Jim and Joanne. They write, indeed, we are tiny in the context of the universe, but our chutzpah should be limited by the fact that an object much tinier than we, the COVID spore, is
That's very good. Yeah, that's so true. On the other hand, we could have done a lot better, and we could have done a lot worse with the COVID. So so this is a nasty pandemic, but the pandemic of 1918 was much worse, and the Black Plague was much worse, and historically there have been much worse plagues. So the fact that we had sophisticated responses, we're going to have a vaccine, and so forth, is an indication of our increasing control of nature. So we have humility, but we should also have chutzpah, and we should have enough chutzpah to realize that we could have done a lot better. If we have the technology to monitor all over the world emerging diseases and identify them and nip them in the bud before they spread exponentially, and we just didn't do it, not because we couldn't scientifically, but because of political stupidity and refusal of people to cooperate to do that job. and I hope we'll do better in the future. I hope this may, among other things, may be a learning experience.
Thank you. Joe has a question in voice.
Hey, Frank, it's Joe Logan from Pennsylvania. Enjoyed your
Hello.
lecture again.
Thanks.
How are you? Before I go to my question with regard to your comment on the virus, I think we would do a lot better if we didn't encourage the virus to get into our world by
Yes,
getting
of
to
course.
nature that we shouldn't be involved in. So that's a whole other issue. I really thought it was.
There's a saying that I slipping my mind who originated it, because I had a wrong idea. Like, but I think it's Alexander Pope. He said the against stupidity, the gods themselves struggle in vain.
Intend.
Yeah.
Very good. I really enjoyed your lecture, as I usually do. My question was, what did your work teach you about human death?
Human depth or death?
Yeah.
DEPTH?
Death, our immortality.
Our death.
Death. Here's the context. The context
Nothing good. Yeah.
The context of the question, before you answer your question,
Yes.
the context of the question is many of the performers who I admired, who are now in their 70s, have now written works where they're much more reflective on their mortality. Springsteen's new album, and certainly Bob Dylan's new album, they're very reflective on the life they lived and the fact that they're going to die, right? So what I love about your lecture and Lawrence's lectures, and anytime I get in front of some physicist, I realize how humility, how little I know, and how exciting it is to just get a grasp of how insignificant we are and how beautiful that is and intimidating that is. But then that leads me to the next question, is like, well, I'm here for a period of time and then I'm going to die. What does this all mean? Matter and energy. I mean, the matter of who I am is going to die. What happens to the matter and the energy? I mean, can you comment on that on a physical level, a physics level?
Well,
good.
One thing, okay. There's a wonderful quotation from Einstein, which I could dig up, but let me not, but I'll give a paraphrase of it, which is that the deep study of the universe tells us that the idea, that the concept of self is an illusion, that really the boundary between self and not self is not fundamental. And I think that's emerged even more clearly in the physics that he didn't know about, the deep quantum theory and understanding of the fundamental interactions that we achieved in the later part of the 20th century. So part of the humility is realizing that it's or part of the lesson is, well, let me put it crudely. The one thing that you learn, and part of humility, is that your own death is no great loss. The world will keep going, and if you think about yourself not as an individual, which is kind of an illusion, but as part of a community, a part of a universe, part of something bigger, then the individual death of your body is less disturbing, perhaps. Now, I realize, and that there's a kind of sour grapes to that, yes. And if I could live much longer, I certainly would. And I try to take care of myself. I eat vitamins and take exercise and so forth. And I do think that the death of minds and people that have established loving relationships and learned a lot and so forth is a great tragedy every time it happens. And something that should be high on the agenda of science to improve the human lifespan. And I think that'll happen on the time scale of maybe decades, maybe centuries, maybe a few centuries. But if there's not a catastrophe of climate or nuclear war, I think people will live longer, be smarter, and have more able machine assistants in the future. And that's another comforting thought, but also it'll change the whole perspective on this issue of death. So so those are some disconnected remarks, but I hope they give you a sense of how honest understanding of the physical universe plays into that question. And so on the one hand, it really does erode the distinction between self and not self. What is the that's a rule of thumb that we learn as babies. When we're babies, we learn that there are certain things that we can control by our wills, our bodies, or we can move around our hands and things like this. And that has to be learned, though. Babies don't learn it, and babies learn it because it's useful and it's an important distinction about how they interact with the world. But as we grow up, and especially if we study science, we learn that fundamentally we're made out of this. The self is made out of the same kind of stuff as the rest of the universe and interacts with it. And at a fundamental level, in quantum mechanics, you have to include the interaction of observer and observed. Otherwise, you can't get a consistent description. And we learn that the universe is vast. So all those things sort of make the self seem less important.
Great. Thanks, Frank.
But it's complementary. The self is still very important. Every self is still important. And it would be good if we could keep them going for longer, for sure.
Yeah. Thank you. Thank you. I look forward to reading your book.
Before there's a number of questions, but one, Judy was asking if there's going to be a recording and
an audible
an
version of the book.
Oh, an audible version of the book.
Mhm.
Oh yes, it's there. An audible version is it's definitely. I don't know when it might become available at the same time. I don't know, but it has been recorded by a very excellent professional at doing that. We were given a list of candidates, and we got one of the best in the business, I think, to do that. And I should say, I showed you that graph of the GDP.
Yes.
That's the one and only figure in the entire book. So unlike A Beautiful Question, I think, which really lost a lot in the audio form because it was so visual, Fundamentals does not lose much by going into audio. And yeah, so if you prefer that's certainly a recommended alternative.
Well, now that you've mentioned a beautiful question in your book, the next question is derived from that, from Steve and Evie Lawson. Thanks, loved A Beautiful Question, with concepts like the Heisenberg uncertainty principles, which tells us that we cannot know certain things, at least not at the same time. The momentum and position of a particle. Spooky action at a distance, seemingly to require super light speed in contradiction to Einstein's law. Paradoxes like Schrodinger's cat, the twin paradox, and many others suggested by modern physics and multiple dimensions that are suggested by both physics and the math used to describe it. What do you understand reality to comprehend? The things that the senses can perceive? Or does reality include the things that we either do not or cannot know or understand given the current state of our brains?
Well, okay. Our senses are very limited, that's for sure. We use microscopes, telescopes, magnetometers, accelerators, all kinds of tools in order to spectroscopes, and well, I could go on and on. Squids, superconducting, and quantum interference devices, one I'm very fond of. So we can augment our senses in many, many ways. So there's no question that our ordinary, everyday, unassisted sensation of the world is very, very partial and impoverished. And that's one of the big messages in it's a whole chapter really about that. One of the big keys to understanding reality. Now, this question mentioned a number of things about spooky action at a distance and uncertainty and all these words that seem to indicate that faster than light, something or other, indicate that our understanding of the world is somehow very shaky, and that but it's not. If you, I think some popularizers of science have done a real disservice by making it seem more mysterious than it is. The quantum world is strange. There's no question about it. It does not. It's a very different world construction that you're led to with accurate instruments than you construct as a baby and just interacting with matter here on the surface of the earth at modest temperatures and so forth. In the book, I very much talk about that. It's a process of being born again. You really have to reconstruct your understanding of the world, but it is understandable. It is, as Einstein said, the amazing thing is that it is so comprehensible. And yeah, so don't be, when people, and it was Einstein himself who talked about spooky action at a distance, but Einstein was a very great man, of course, and came up with some brilliant ideas, no question, but he never understood quantum mechanics properly. And if you do understand it, it's not spooky. It's weird, but not spooky. It's so the predictions are perfectly rational and definite, and the proof of the pudding is transistors and Zoom and communication like we're having. I mean, it would be literally inconceivable without profound application of the principles of quantum mechanics, and it works mostly. Sometimes Thomas and Patty go offline, but basically it works.
We're here most of the time. So, the next question is from Ben. He writes, you state that there are few ingredients, but it seems that there are various subatomic particles, some of which are at least partly mysterious. How can this be squared with the idea that there are few ingredients?
Well, okay. So there are very, very few ingredients. But first of all, okay, there are a couple of answers to that. One is that the ingredients that make up what I call normal or ordinary matter, the stuff that we're made out of and that you study in chemistry and biology and all forms of engineering, that stuff has very few ingredients. It has photons, electrons, quarks, and gluons. That's it. Okay. And two kinds of quarks. So if you get a little more refined, you want to have gravitons so that there's gravitational force. But really, that's it. There really aren't that many ingredients. If you start to expand the list to include particles that are involved in some branches of astrophysics and in powering the sun, you need to bring in neutrinos and some effects in radioactivity. Then you have to bring in neutrinos. Then if you want to do justice to what happens at high energy particle accelerators, you have to introduce quite a few other particles, because they're at accelerators, people discovered that there are a couple of dozen highly unstable particles, so they don't play a role in everyday life. They're extremely unstable, and you have to go to great lengths to produce them that we don't understand properly. And as I said, if you count them all up, there are a couple of dozen. But it depends how you count. It's like if you have a die, is that one thing or six things? Well, if you count the numbers, there are six different numbers on the die, but it's one die. We understand that the six are all aspects of the same thing. And due to the concepts of symmetry, we learn that the particles, many of the particles are like different sides of one die. And so we're trying to construct a kind of super structure, a die, where you can see that all the particles are actually different aspects of one thing. And that's the whole program of unification of the forces and particles, which is hypothetical because we in part because we don't have all the information that's necessary. The experiments get very difficult, but there's nothing against there's no compelling evidence to crush our dreams that there really is a unified description where we'll see that ultimately we can understand all the particles and all this apparent complexity on the basis of one structure that has different sides.
Great.
So different manifestations. Yeah.
Thank you. David has a question. He wrote,
and in fact, I can take that a little bit further. Well, maybe I shouldn't, but just to say that it's almost in the concrete realizations of these ideas, it really is almost literally like a die with different sides. The particle, we have small extra dimensions in which things can move, not freely, but what you're seeing as different particles are actually just the same kind of particle in different places in those extra dimensions, so-called internal spaces. So that's a concept that's very powerful and brings unity to apparently very diverse phenomena.
David wrote, Professor Wilczek, I appreciate your listing complementarity as a key to reality. I also worry, I feel this concept is easily misused to justify muddled thinking and mystifying language.
Yeah, it is. Well, that's an aspect of complementarity. It has both good sides and bad sides. Right? Yes, but yes, it can be abused for sure. But that I think the benefits of bringing it in and consciously applying it in terms of fostering tolerance, fostering imagination, far outweigh the dangers of getting confused sometimes if you think in muddled ways. That's complementarity does not repeal logic or rigorous thinking. It in each view, you should try to be completely logical and carry out its implications fully, and make sure it's consistent with itself and so forth. So that's that kind of mental hygiene is still very much in order, and complementarity is not meant to abolish that.
Betsy wrote, Friedrich Schiller, folly thou conquerest, and I must yield. Against stupidity, the very gods themselves contend.
Oh, Schiller. Yeah. Okay. Yeah. Very good. That's right. Yeah. That's right. Yeah. So Betsy is my wife. You may Betsy Betsy Devine, and she's a very active citizen of Wikipedia, the Wikipedia universe, and is very good at using it, and has also done great service in keeping in the hygiene of Wikipedia. Which,
Why, thank you, Frank.
which, by the way, is a terrific contribution to human culture, I believe. Yeah. One of the things that the 20th century and the 21st will be remembered for is this gigantic community effort to organize knowledge.
Gail wrote, you say complexity emerges. Would you care to discuss the law of entropy, perhaps why it is the case?
Okay, this could get very technical very rapidly, but basically the concept of entropy is a rigorous way of measuring the disorder of a material. So materials at high temperature tend to have high entropy, for instance. Other things being equal, the entropy of materials increases because they do more probable things. They do things that are more probable, and if there are more ways of doing things that are roughly the same, that makes them more probable. It also makes them more high entropy. So that's the law. That's a very, very schematic description of the logic of the second law of thermodynamics, which I'm not sure gives you a very good flavor of it, but it just says the most likely thing happens. And you follow that logic out together with the other laws of physics, and you find observable consequences, like the fact that if you have a hot substance next to a cold substance, the temperatures will tend to equalize. And okay, so I'm not sure what the question was directed at, but let me take it in a certain direction, which is one very interesting question is, okay, with that in mind, how can complexity emerge from simple beginnings and very generic beginnings and high entropy state, which was sort of thermal equilibrium, where everything is the most likely kind of blurry, messed up thing, into the very elaborate and complex structures we find around us today, and which we are. The answer to that is that it's the universe actually, and it's spelled out in fundamentals, and I think almost a unique way, because I think even very few professional physicists understand this problem properly. There's a lot of confusion about it and wrong things, but basically the statement is that despite appearances, the Big Bang, which was very hot and very apparently high entropy thing, was high entropy as far as matter was concerned, but was very low entropy as far as gravity was concerned. Gravity would like to clump things and make the universe very non-uniform, but the early universe was very uniform. So it was in a very unlikely state as far as gravity is concerned. And the subsequent history of the universe at very low resolution, but the great theme that's been playing out in the evolution of the universe ever since has been gravity trying to restore its share of the entropy. So things becoming more likely states of what gravity should do, and gravity wants things to clump. So you start with a very uniform distribution of matter, and then ever since it's been trying to clump and forming stars and galaxies, and that unleashes new potentials for matter. And you trade low entropy in the gravitational field for higher entropy in the gravitational field and lower entropy in matter. So the overall entropy increases, but you can make complex parts, but it's not uniform. There are places like our human bodies where the entropy is very low, and ultimately that's because gravity has enabled stars to shine and make energy and organize things and make small parts of the universe that are compact in the midst of the vast empty spaces that constitute most of the universe. And Well, that's what's properly explained in those chapters about cosmic history as an open book and complexity emerges.
Great, thanks.
So Frank, I have a comment.
Mm,
Um,
yeah.
We had a really wonderful salon last week with a medieval scholar on the collection from the cloisters in New York and
Oh, yes.
highlights of the collection. And he showed us a very beautiful little book of hours. And it occurred to me when he was describing this, that your new book is somewhat of a book of hours in that
Oh, well,
you can
it
open.
would need two, it would need two more chapters or
Yeah.
or 14 or yeah.
But you can open it up, and each section is meditation on the universe. And I think, in the book of hours in medieval times served to help people meditate
Yeah.
on the concepts of the time. And I think that's what your book does. And I really love it.
Well, thank you. I've never thought about it that way, but yeah. When I picked 10 very consciously because I wanted to have, well, there are 10 commandments,
Yeah.
and I was talking about fundamentals. So, the other thing is, all these books for dummies, they have lists of 10 at the end, which I found very kind of inspiring. That's a number that people can relate to, and it's neither too big nor too small. And it was also for me a discipline to try to pick out, of all the things you might say, that what are the most important things that people who want to understand their world better should know from the point of view of fundamental science. And so it was a discipline to pick out a small number of principles like that. I actually picked out 9 to begin with because I wanted to have room for one more, and complementarity, which brought it all together. Complementarity was the 10th. So that, so I had, and well, I'm very happy with the list. Actually, I was thrashing around for a long time and trying to construct this book. The original proposal, I think, was 4 years ago or something. I have been working on it continuously since then, but I was kind of thrashing around until I had this concept of 10 keys and the discipline of focusing on what they should be. My initial list was much more technical and sort of much more standard for popular science. Okay, I'm going to tell you about the second law of thermodynamics. I'm going to tell you about Coulomb's law. But I decided that the profound things that people would like to explore and that have more meaning are these kind of quasi-philosophical general principles that fundamental study of reality reveals.
As a final question, Frank,
Yeah.
what are you most excited about for 2021?
Well, I have a motto, which is think, play, repeat. So my life keeps going on. I keep doing that over and over again. I'm hoping to make, I guess I'm excited about a lot of things. I have in research, I have been developing a new way to visualize and play with quantum mechanics. That's fun, and I think will turn out to be useful. Because it's notoriously difficult to visualize and make simple models of how quantum mechanics works, and now it's becoming a kind of a crisis to have that kind of intuition as people want to build quantum computers and think about how to use them. So I've kind of boiled it down to very simple things, and another thing that way of thinking opens up is ways of playing with time. Quantum mechanics is a very funny thing. I don't. it's kind of elusive in quantum mechanics, and you can easily construct questions like, I mean, suppose there were a race of individuals based on matter where time ran backwards according to according to our measure of time. As I told you, the laws of physics are symmetric between going one way and going. The fundamental laws are symmetric between going one way and going the other way, and so one would think that it would be logically possible to play with such kinds of creatures, or if we have eventually quantum computers, to actually build things where time runs backwards effectively, and that are complex. And how do you formulate what would it look like to interact with such things? There are all kinds of paradoxes that seem to arise, but if you have a mathematically consistent formalism, it can't produce contradictions, it'll produce enlightenment. So I've been working on that. So I guess, you know, that's probably the weirdest thing that is just opening up in my mind. So that's what I'm currently the most excited about. But I'm very excited about the prospects of designing axion antennas, the prospects of understanding the application of quantum mechanics to things, in particular gravitational waves, that have been analyzed only classically, really, and to see evidence of how quantum mechanics affects gravity and vice versa. So well, this is, you know, I could give 5 or 6 salons on what I'm hoping to do. I'm also for many years I've been playing with the idea of writing a mystery novel.
Yes.
Yeah.
How is that coming?
It's really now it's really coming. I've learned enough from the discipline of writing fundamentals and writing these Wall Street Journal columns. I've learned how to simplify and sort of turn writing also into something more algorithmic. And now I've simplified the plot and it's rolling. And so I hope maybe this time next year we'll be talking about, or maybe the year after, we'll be talking about Attraction of Darkness coming out.
Oh,
That's
great.
great. We're looking
Yeah.
forward to that one.
All right. For those of you who don't know, this has been a long, it's the idea that the leading idea is that there are 4 collaborators who do spectacular work in science, and it's clear that they should get a Nobel Prize for this. But according to the rules of the Nobel Prize, at most 3 people can share, and so somebody's got to go, and then one of them dies, and it looks like suicide, but was it really? That's
Stay tuned, huh?
Yeah.
yes, right.
Frank, this is great. A great evening with us. Thank you.
Well, thank you. Thank you for the opportunity. I hope that wasn't too painful for you.
Oh, it was great. No.
Fantastic.
Anyway. All right. Okay. Anyway, if you like that, there's much more in the book. All right. Okay. So thanks.
Thank
Bye
you
for
so
now.
much, Frank.
Sure.
Thank you.
Thank you, Frank. We'll be in touch.
Bye-bye. Okay.
Bye-bye.
Bye now.